Hi folks, we're now going to move on to the next two questions in the October 4th lesson, and in those questions you were asked to come up with everything you knew about exponential functions and inverse functions. Okay, so let's talk about exponents and exponential functions here. Okay, so the first time you would have dealt with exponents would have been with positive integer exponents. Okay, in which case, whatever the exponent was, you just multiplied that number by itself n times. Okay? Then from there, you kind of took it a little further. What does a zero exponent mean? And you probably did some little investigation to show that any number to the exponent of 0 is equal to 1. Of course, with the caveat that the base can't be equal to 0, but for any other base to the exponent of 0, it's always equal to 1. Okay? And then you started to expand that now to negative exponents. Okay, so I'll go down to this one here. So if you have, a to the negative 2, you've now expanded it to all integers, and you realize that the effect of the negative, is to just give you the reciprocal of that power, a to the n. Okay, so now from having all integers accounted for, you then move to rational exponents. Okay, and then you started with simpler rational numbers of the form 1 over n, and you realize that exponent of 1 over n is just equivalent to an nth root. Okay, and then we'll go down to the bottom here. Well, what happens when you have a general rational exponent? Okay, and you realize that you can combine part 1 here and part 3, okay, by using one of the exponent rules that power of a power is just equivalent to multiplying the two exponents. So I could rewrite this power with an exponent of m over n by first, in this case here, taking the numerator power and then taking the one that comes for denominator, 1 over n, which is your nth root. Or I can do it in the other direction. First take the nth root of the base and then to the exponent of the numerator. Okay? And here we realize that this can be defined for all x and r. Now again, there is a little caveat here that if the base is equal to 0, the exponent can't be equal to 0. So there is a little bit of a 0 over 0 is not defined. Okay, so you may even want to sort of write that in as a reminder. Okay. Here we have our exponent rules, okay, and we're going to see that they are actually going to come into play, fairly soon in another context. So keep those in mind, okay. And we've already used the third exponent rule to be able to come up with a way to define rational exponents. Now here, when I say that this can be defined for all x and r, okay, well, one thing to keep in mind here is that what we haven't defined yet is what it means to take an exponent, which is an irrational number. So what does the expression 2 to the exponent pi represent, or 3 to the exponent of root 2? Okay, and that's beyond sort of the purview of these courses. So to get a sense of how one does this, well, you'll have to wait till you get to your university calculus course. Okay, but we can define these expressions, and your calculator can help you get an approximation for them. Okay, so this is the basics on which we work with exponential expressions. Okay, now from there, again, you just stick a y equals in front of an exponential expression, and then you've created a function. In this case here, what we call exponential functions. Now, when we're talking about exponential functions, we limit ourselves to bases that are greater than 0. Okay, because we realize if you have a base that's negative, well, you run into problems. So right away, any fraction that has an even denominator, so 1/2, 1/4, 1/6, won't be defined. So a lot of issues occur when we've got a negative base. Okay, so we limit ourselves to positive bases, and we also don't bother with a base of 1, because 1 to the x, well, that's always going to be equal to 1, not a particularly interesting function. So when we limit ourselves to these bases, we realize that these functions have a few things in common. They all have a domain in R. They all pass through the point 0, 1, because regardless of what the a is, Okay, when I take to the exponent 0, I know I'm going to get 1. Okay, they all have horizontal asymptotes of y equals 0. We'll see in a second what that looks like. Okay, and we know that these numbers will always be positive. Okay, because if my base is positive, regardless of my exponent, the output is always going to be positive. Okay, and in the same way that we group together different functions, so for example, polynomials are grouped into even and odd degrees, and we saw that rationals were grouped based on the degrees of their numerator and denominator. It's the same for exponential functions, and we usually group them as bases that are greater than 1, and then bases that are fractional between 0 and 1. Okay, and so here, the best way, I guess, to describe this is to use a graph. Okay, so we know that it passes through 0, 1. We know that it's always positive. Okay, it's increasing over its domain. Okay, and here we see the end behavior that while it does have a horizontal asymptote, it's a little different than those rational function horizontal asymptotes, because here you see that the asymptote only applies to the end behavior as x goes to negative infinity. As x goes to positive infinity, y also goes to positive infinity. Okay, and our second grouping here, when a is between 0 and 1, we see that the function has a similar but sort of opposite behavior. Still has that horizontal asymptote, however, it only applies when x approaches positive infinity. As x approaches negative infinity, y approaches positive infinity. Okay, and here we see that it decreases over the domain, but it still passes through the point 0, 1. Okay, and as with any other function, you can transform them with stretches and translations and reflections, just as you would any other function. Okay, and another thing that you would have worked on last year is some of the applications of exponential functions, of which we saw 2 in the first 2 examples in this lesson. Okay, so exponential growth and decay problems, compound interest, half-life, any kind of appreciation or depreciation, okay, can be modeled by these exponential functions. Okay, and the most common version of the function that we work with is this one here, where we have our initial value times some power where the exponent is in the where the variable is in the exponent. Of course, we saw another variation of this, okay, in our half-life problem, where d represented the time that it took to get the half-life. Okay, so these would have been all the basic properties of exponents and exponential functions that you would have studied from grade 9 to grade 11, and it is expected that you're well versed on all of these. Okay, that's it for now.